Lab Guy here. Today, let's take a break from horizontal scan circuits and take a look at another section of the chief. Today I want to look at the high voltage power supply and bias network for the RCA 2F21 monoscope tube. This is the tube that contains the Indian head test pattern. There's a metal plate called the picture electrode at the end of a 5-inch tube, and on that plate is printed the image that we want to scan out. It's scanned by an electron beam in exactly the same way as a camera tube, iconoscope or Vidicon. An electron beam generated by the gun is sent towards the front and swept over the picture electrode, generating an output voltage. Where the electrode is bare, current will flow and a voltage will be produced. Where there is ink, the electron beam is blocked and no current will flow. The device is actually digital. The image is screen printed, and the bit of grayscale that exists in it is actually very fine screen printed regions which are printed at various densities to produce different grayscales after the output signal is low pass filtered. We'll get into that later in the video amp chain. So back to this device. When the electron beam is scanning the picture electrode, it can build up electron charges on the ink, and it can knock out secondary electrons out of the bare metal. So there's an electrode located just behind just before the picture electrode. I'm not sure if it's a ring around the image or a very fine mesh, probably the latter, called the collector. It is operated at 50 volts above the electrode voltage of the picture electrode. I'm operating the picture electrode at 0 volts and operating the cathode at minus 1000 volts. If you look at the data sheet for the tube, you may become confused because all tube data sheets reference to the cathode. Therefore, this cathode would be 0 volts and this plate would be 1000 volts. Well, I challenge you to hook a 1000 volt plate to the input of a transistor. So back to this upside down circuit. We're outputting at a 0 volt reference level. So to get the electron gun to work, the first thing we have is a 6 volt AC transformer which comes over and operates the heater, or what is commonly called the filament. I prefer the term heater as it is more accurate. It heats a cathode to the point where electrons boil off of it, and it is attracted to the second anode by way of the positive 1000 volts on that anode. Now we see that this one is 0 volts and the cathode is minus 1000 volts. Therefore, this electrode is positive 1000 volts above the cathode. The electron the electron beam is controlled in its intensity by grid 1, which is another electrode placed just before the cathode, and it has a pinhole where the beam originates. If we make this electrode more negative than the cathode by about 50 or 100 volts, we can cut off the electron beam or set it to the level that gives us the desired output level that we'd like to see. The remaining electrode is the focusing electrode, which operates at a high voltage of about minus 700 volts here and plus 300 volts relative to cathode. It's adjustable by plus or minus 50 volts so that we can focus the beam. It operates in a way that a charge is formed between the second anode, which is two pieces, one on each side of this. These are cylinders, not grids. And this cylinder sits between the second anode cylinders and forms an actual electron pinch point, which behaves exactly like an optical lens, which lets us focus our beam to a spot. So that is the general operation of the tube, if you can imagine it from this schematic symbol. So getting into the operation of this, we start on this side where we have a scan OK sensing circuit that says that we are scanning in horizontal and vertical, and they're both OK. In that case, turns the relay on. This applies 12 volts to our voltage regulator, an LM317. We set the output voltage here to the required input voltage of this MCO F10 power supply to give us 1200 volts out. Now this power supply is 3 watts and can output, it is specified to output 1000 volts at 3 milliamps. But you can run it at a higher voltage output if you reduce the current so that you don't exceed its power rating. So I've designed this resistor string, which goes in a circle like that, to draw 1 milliamp. It's a 1 milliamp loop current, 1000 ohms per volt. So the first resistor in the string at the top is 3K. This resistor, though it's hooked to a 1200 volt power supply, has a 3 volt drop. It will drop the 150 to 147 volts. Now, how did I get 150 on a 1 kilovolt output power supply? This point in the, call it the middle, a mid tap of the electron divider, is grounded. That is the reference. The power supply relative to ground is floating. So from this point north, we have 100K, which is a 100 volt drop, so that we, when it's centered, we get our approximate 50 volt collector voltage. These two resistors take care of the additional 50 volt drop to give us the 100 volts at the top of this 100K resistor. This is a 47K and a 3K, which together give us 50K, 50 volts. Following on down through the divider now, we're going from ground, we're going south of ground now, and we start dropping 620 volts here, 33 more volts here, so for a total of about 650 volts, negative, which is the top of our focus control, which also 100K, he drops another 100 volts so that we're at minus 750. We go through another 33K and a 220K, which is about 250K, so there's 250 volts more dropped to the cathode level, which is our minus 1000 volts. To bias an electron gun, you set the cathode to anode 2 voltage first before anything else and make it 1000 volts. Now this could be 500 volts and this could be minus 500 volts. Then these voltages would all be scaled accordingly. From the electron gun's point of view, there's no difference. It's still 1000 volts from here to here. Back to this chain. We keep coming down and we've reached the cathode. In the same way, which is the tube's version of ground, correct? We need the grid to be more negative. Therefore, we keep going south and we drop another 100 volts, which gives us approximately 50 volts in the center here, which we couple to our grid, and around 50 volts you cut off the beam. If you want the beam to turn on, you dial it up a little bit until you get some beam. Also, the blanking signal from another circuit will be sent in here, a pulse of about anywhere from 10 to 30 volts, AC coupled in, and added to this DC voltage at this point. That's why there's a resistor here. From this thing's point of view, over here, anywhere over here, is ground. Okay? AC ground. So the signal on here would come through here and would travel to here and be shunted to ground through this capacitor, because we don't want any signal on the cathode. We want this to be a steady DC voltage. So this keeps AC signals off of this line. This isolates this pot from our signal so that we don't add our signal into this chain and cause it to bob up and down. This is just a square wave pulse that is off, that will generate a negative pulse during the blanking regions of the video signal. It's produced initially in the sync generator. Then we come on through our beam control and back around to our power supply. The power supply is filtered on the output with two 1800 picofarad 3 kilovolt capacitors in series. Since this is 1.2 million ohms all the way around, or 1200 K, 1200 volts. 1000 ohms per volt. Each K is 1 volt. And 1 milliamp, which is 1/3 of the power supply's full capability. Now, I designed all of this based on the tube data sheet and the EMCO power supply data sheet. That's wonderful. This is what I call on paper. So before we build this thing, waste our time putting it all together to find out it doesn't work or it's pulling too much power, let's breadboard just this stuff here. The tube, when connected to this chain, which is running 1 milliamp, draws literally no current. The tube's impedance is so high. Notice there is no physical connection from the cathode to here except a very faint cloud of electrons. It's in the megohms. So there is no additional loading from there to there. Now there is, when I put my meter here, that's 11 megohms across here. But that's 1,000 ohms, 1,000 K or 1 meg with 11 more megs in parallel. Very light loading. So the meter doesn't affect this when we make the measurements. So that is the high voltage side. Now, another aspect to keep in mind is that the 6-volt heaters are sitting here stuffed up inside a little hollow tube with a flat plate on the end, and they are sitting, they're floating on their own non-related voltage to any of this, running 6 volts through the heater. And therefore there could be, and this is at 1,000 volts negative, to prevent this the cathode from arcing to the heater elements, I pull the heater down to the minus 1,000 volts using a 100 K reference resistor fed to the center tap of the transformer. This balances the high voltage across the heater so you don't have a hot side and a cooler side. And that's to prevent arcing and for other safety reasons. We don't end up with our 6-volt, this 6-volt circuit tied to anything else in the unit. Therefore, we can't have a fault here that will feed back into my solid state and blow everything up. And that is essentially the entire circuit. I will, at the end of this video, I will post this schematic as a full frame in the video for you to study. Use your pause control. So, at this point, let's move over to the workbench and look at the actual circuit. Here we see the physical implementation of the circuit we were looking at on the schematic. I would like to correct one error I made in the description. The beam control has a 100 K resistor paralleled with it because we need a 50 volt drop there. By paralleling 100 K fixed with my 100 K pot, we get a 50 K pot, giving us the required 50 volt drop. Now, continuing, let me just go through the parts and point them out. Here's the 3K resistor, the 47K resistor, the 100K shading control, which controls the collector electrode, the ground tap that was shown on the schematic as ground is the meter ground. From there is our 620K in series with a 33K, the 100K focus control, the next 33K, a 220K, and the 50K beam control, and back to the power supply. That is our loop. So, the first thing we will do is we will set this by setting the voltage at the top of the I can't remember the name of it the shading control to the indicated 100 volts. So we turn on our power supply and our meter says 101 volts. Considering these are 5% resistors, I'd say that is pretty accurate. That is pretty accurate. Now, that's 100 volts from this ground in the middle of this string to the top of this resistor. Because it's a 100K resistor running 1 milliamp, it will drop 100 volts. So we could do some fine twiddling with our power supply voltage and make that exactly 100 volts if we wanted to, and I'm trying to. There we go. So there's no need. The resistors are not that accurate. So that is our 100 volt point and our ground point. So the next interesting point to look at is the top of the focus control. I'm going to risk my life and do this. And it is at minus 650 volts on the schematic. Let's see. Minus 637 is not that far off. Again, 5% tolerance here. The bottom of that control is minus 750. Let's see. The reason I'm not getting zapped is this loop is not grounded anywhere in the house. It is a floater, in the famous words of Austin Powers. We've got a floater. So there's our minus 750. So going on down to the top of our beam control, this should be just about minus 1000 volts. And I'll take 985 volts any day. A little bit of floating going on there, but none of this is out of range or out of tolerance. This is all good. And then the very bottom is our 1050 volts as shown on the schematic at the bottom of the beam control. Our circuit is working. Now, let me read the meters on the power supply. We are running approximately 10.5 volts of input DC to the F10 high voltage power supply. It is consuming just under 500 milliamps, probably 460, 470 milliamps going in, which is about 5 watts going in. We know we have 1200 volts going through our chain, and we are drawing about 1 watt out. So we're getting about 30% efficiency. So there might be some heat involved. Let's find out. We look at our power supply here. Well, first let's see what ambient is. Ambient temperature here is 20 and a half degrees Celsius. The power supply is running 4 or 5 degrees above that and is relatively steady. Looking at our resistors, they are running a couple of degrees warmer than ambient as well, but virtually indetectable to the finger, which I am not sticking in there, ground or no ground. So as you can see, we're not overheating anybody. We're in very good shape here. The power supply is running at a comfortable about 25 degrees C. I expect it to gain a couple of degrees once it's inside the cabinet with no cooling. I don't know if we'll need cooling in there yet. This is unlike the same class of power supply I used in the Philocam project, which is temporarily on hold while this one's being completed. And it was running its power supply at full load, and I was having heat issues with that power supply. So in this test situation, this circuit is working. Now, as I said, the tube elements add no load to the resistor string, so this is a valid test. The number of microamps that will be pulled by the tube, by the electron beam in the tube, are insignificant. And even if they have a small effect, we adjust the voltage of the low voltage power supply to compensate for that. So this is the DC bias string for the 2F21 monoscope tube in the Chief. So now you know. I know you've wanted to know this. I've been dying to know this. This is the first time I've heard about it myself. So I'm glad I made this video so I could find out. I hope you all got something from it, and I hope this inspires you all to go out and build something yourself. As SV Seeker channel likes to say, what have you made today? This is Lab Guy out.